Now, we're not going to get deep into physics and formulas here. There's just a couple of simple things I want to point out. Now, this is a copper atom, and in the center we have what are called protons, which have positive charges. These smaller balls on the outside, these are electrons, and they have a negative charge. Now, in this little world of atoms, when you have particles of opposite charges, plus and minus, they attract one another. When you have particles of the same charge, whether they're both plus or both minus, they repel or push away from one another. Now, what I want you to do is focus on this one electron here on this outer circle. That one electron is the furthest one away from the center, and so it is the weakest bound electron out of all of them in this whole entire copper atom here. And that means it's the easiest one to knock free. That is exactly what voltage does. When we apply voltage to a wire, it propagates throughout the entire wire as an electric field, and that electric field is what knocks that electron free. And so what we end up with is what's called a free electron. Now, in a copper wire, there's billions and billions of these copper atoms, which means we have billions and billions of these free electrons that we can now move and make use of. Now, in a direct current or a DC current, all these free electrons are flowing in one direction, like water molecules making up a river that flows in one direction. And as these electrons travel through the wire, they're bouncing off of each other, they're bouncing off of other atoms, and that causes atoms to vibrate. And so when these atoms vibrate, they generate heat. That's why sometimes when either voltage or resistance is not properly regulating the current, we end up with wires that could melt or even cause fires. The heat is so intense from these electrons moving too quickly through the system. Now, a pretty good analogy on visualizing how a DC circuit actually works and how current flows through it is to imagine a 5-lane highway, bumper to bumper traffic, and everybody is at a dead stop because the town that this highway goes through decided to put up a traffic light, and everybody's sitting at a red light. Now imagine each one of these cars is an electron, and it's just sitting there, and this represents our open circuit, right? So there's some control preventing the system from running, or the motor, or the lights from coming on, or whatever the case may be. Now, as soon as that light turns green, it travels and propagates at the speed of light. And so everybody sitting there can see that green light at exactly the same time. And this is exactly what happens when voltage is applied to an electrical wire. All these atoms can see that voltage at the same time. And what happens when everybody sees the green light? They all step on the gas pedal at the same time, and their cars start to propel forward. And so that's what voltage does to electrons. All these electrons see it at the same time, and they all start to propel forward. And in direct current, they're all traveling in the same direction, just like all the cars on the highway are traveling in the same direction. Now, with each one of these cars or electrons, we have an engine carrying with it a certain amount of energy. And so as this energy is being carried by these cars, it's being delivered to a component in the form of power or wattage that we're actually using to make work happen. So that is lighting up our light bulbs, turning our motors, and so forth. And so the same thing is with electrons. These electrons are carrying a certain amount of energy into a component at a certain rate, and that is the current that is delivering power and wattage to our components to operate them. Now, an alternating current is a little bit different. Now, a pretty good analogy on how an alternating current works is one of these Newton cradles. Now, we've all seen these, we know how they work. When you lift that first ball up high and you hold it there, what you have is a potential difference. We know when we release that ball, it's going to come down with a certain amount of energy and slam into that first ball. Now, potential difference, that's what voltage is. So when we release this ball and we realize that energy, it's going to slam into one ball. That ball is going to put that energy into each successive ball next to it, and eventually at the other end, as we know, the other ball will swing all the way out, showing the result of that energy being transferred through all the balls, and that is the power or the wattage that's being delivered to the component. Now, unlike in a direct current where all these balls or electrons are all traveling in one direction, in an alternating current, these electrons are traveling back and forth in an oscillating fashion. So under Newton's cradle, when that last ball comes swinging back again, it's going to do the same thing. It's going to transfer all its energy through each one of these balls, come out the other end. And so electrons are doing the same thing. They're transferring their energy to each other from one end to the other, oscillating back and forth. So what I'm going to do now is I'm going to add a light bulb to this, and we're going to put it into motion to see how power is delivered on an alternating current. When the current's flowing in one direction, when it reaches that full potential, we could see the light bulb starts to light up as it's receiving that power. But as the current reverses and go back in the other direction again, our light bulb dims down until our current is flowing in the opposite direction at its full potential, and our light bulb lights up again. And so back and forth we go, and we can see here how our light bulb is on and off, on and off. Now what we're looking at here is an alternating current at 1 or 2 cycles a second, let's say. But an alternating current is usually delivered at 50 or 60 cycles per second, depending on where you live in the world. So here in North America, it's 60 cycles per second. And so here's what it would look like, the same exact thing we just watched at 60 times per second. And so we could see how our light bulb is steadily lit. It looks nice and even. And this is how an alternating current to deliver a constant supply of power.